Look up at the night sky on a clear, dark evening. You see the steady glow of stars, the silent arc of a satellite, perhaps a meteor's fleeting dash. It feels peaceful, serene, almost unchanging. But that stillness is an illusion. What you are witnessing is not a placid canvas but a cosmic battlefield, a silent storm of unimaginable violence. Every second, your body is being gently tickled by invisible bullets, ghosts from distant cataclysms, traveling for millions of years, carrying secrets from the very edge of reality. These are cosmic rays, the universe's most enigmatic messengers, and they are rewriting the story of everything we know. What if the universe is constantly bombarding us with messages from the farthest reaches of space, written in a code of pure energy? These are not gentle whispers but cosmic screams, particles accelerated to within a fraction of the speed of light, packing more punch than the most powerful particle accelerators we can build. They are fragments of atoms' protons, atomic nuclei hurtling through the void. Some are born in the turbulent hearts of exploding stars, while others seem to come from places and events so extreme that their very existence challenges the foundations of modern physics. For over a century, scientists have been trying to decipher their origins, and the more we learn, the more profound the mysteries become. This journey is not just about cataloging strange phenomena, it is a detective story on a galactic scale. We are about to delve into the evidence to examine the top 25 most baffling cosmic rays ever detected. These are the outliers, the impossibly energetic events that have left researchers scratching their heads in awe and confusion. They are particles that should not exist, with energies that defy explanation, pointing to forces in the cosmos far beyond our current understanding. Together, we will explore these cosmic anomalies, from the legendary "Oh my God" particle to signals that seem to originate from nowhere and everywhere at once. So prepare to have your perception of the universe permanently altered, as we unlock the code of these high-energy enigmas and peer into the deepest secrets of the cosmos. To truly appreciate the scale of this mystery, we must begin with the event that shattered all expectations. On the 15th of October 1991, a single particle descended from the cosmos and struck the atmosphere above the Dugway Proving Ground in Utah. It was not just another cosmic ray. The Fly's Eye Cosmic Ray Detector, a pioneering instrument designed to catch the faint flashes of light these particles create, recorded something that should have been impossible. The data revealed an energy level so staggering that when researchers first calculated it, the reaction was one of pure, unadulterated disbelief. This was the moment the "Oh my God" particle earned its unforgettable name. Think about the energy in a major league fastball, a baseball hurled at nearly 100 kilometers per hour. Now compress all that raw, kinetic force into a single, infinitesimal speck of matter, a proton, a particle so small it is essentially a mathematical point. That was the energy carried by the "Oh my God" particle. It was moving at 99.999999999999995% of the speed of light, a velocity so extreme that in the particle's own frame of reference, a photon of light would have barely been pulling ahead. To put it another way, this single subatomic bullet possessed the energy of a brick dropped from waist height, but packed into something billions of times smaller than a grain of sand. It had millions of times more energy than anything we can create in our most powerful particle accelerators, like the Large Hadron Collider. This presents a monumental puzzle for physics. According to our best models, a particle with such immense energy should not be able to travel very far through the universe. Space is not entirely empty. It is filled with the cosmic microwave background radiation, the faint afterglow of the Big Bang. For an ultra-high-energy proton, this background radiation is like a thick fog. The particle should constantly bump into these low-energy photons, losing its energy over distances much shorter than the scale of our galaxy. It should sputter out long before it ever reaches us. The existence of the oh my god particle means it must have originated relatively close by in cosmic terms, within our local supercluster of galaxies. But what nearby cosmic engine could possibly produce such a monstrously powerful projectile? The hunt for this engine has fueled decades of debate. One leading candidate is an active galactic nucleus, the supermassive black hole at the center of a distant galaxy, greedily devouring matter and spewing out colossal jets of energy. These are some of the most powerful steady-state objects in the universe, and they could, in theory, act as natural particle accelerators on an unimaginable scale. Another possibility is a gamma-ray burst, the single most energetic type of explosion known, the death cry of a massive star collapsing into a black hole. Such an event could, for a brief moment, focus an unimaginable amount of energy into accelerating particles to these extreme velocities. Yet, when astronomers scour the skies in the direction from which the particle came, there is no obvious smoking gun, no recent cataclysm or brilliant active galaxy that definitively stands out. This absence of a clear source is what leads to the most thrilling and unsettling possibility. Perhaps our understanding of the physics governing these particles is incomplete. Maybe there are exotic processes at work that we have not yet dreamed of, decaying relics from the early universe, collisions in hidden dimensions, or phenomena associated with the mysterious substance known as dark matter. The oh my god particle is not just a record holder, it is a profound challenge, a message from the cosmos that our map of fundamental physics is still missing critical and potentially terrifying territories. Just when we thought the oh my god particle was a once-in-a-lifetime fluke, the universe sent another calling card, one so powerful it demanded a name of equal grandeur. In May 2021, sensors at the Telescope Array project in Utah, the spiritual successor to the fly's eye detector, registered an impact of staggering force. This event was so extraordinary that scientists, in a nod to both its immense energy and its enigmatic origin, named it the Amaterasu particle, after the powerful Japanese sun goddess who is said to have brought light to the world. Here was a particle that not only rivaled the legendary oh my god in raw energy, but deepened its mystery in a way that has left physicists genuinely perplexed. The data was clear and incontrovertible. The Amaterasu particle carried an energy exceeding 240 exaelectron volts. To grasp that scale, imagine the energy of a well-thrown stone, but concentrated into a single, fundamental particle smaller than an atom. It possessed the kinetic energy of a falling brick, but all focused on a target a trillion times smaller than a pinhead. This placed it squarely in the same unimaginable energy league as the oh my god particle, confirming that these are not freak accidents but signals of a persistent, though rare, phenomenon in our universe. Their detection, decades apart, tells us that whatever engine is producing these cosmic bullets is still active, and it is operating in our cosmic backyard. But the true enigma of Amaterasu lies not just in its power, but in its point of origin. When researchers traced its path back across the cosmos, they were met with a profound nothingness. The particle's trajectory pointed to a region of space known as the local void, an enormous, desolate expanse bordering our own local group of galaxies. This is not just a quiet neighborhood, it is a cosmic desert, a volume of space largely empty of galaxies, stars, and certainly the kind of colossal astrophysical powerhouses we would expect to be cosmic accelerators. It's the equivalent of finding a cannonball in an open field and tracing its path back to a completely empty patch of sky with no cannon in sight. This presents a monumental challenge to our current theories. Active galactic nuclei, gamma-ray bursts, and even merging galaxy clusters are best candidates for such acceleration, simply do not exist in that void. This directional puzzle forces us to consider possibilities that verge on the realm of science fiction. One theory suggests that perhaps our understanding of the magnetic fields that permeate intergalactic space is flawed. These fields are incredibly weak, but they can gently bend the path of a charged particle like a proton over millions of light years. It is possible that Amaterasu was deflected so significantly during its journey that its apparent origin in the void is an illusion, a cosmic sleight of hand. However, the particle's extreme energy makes this deflection argument difficult to sustain. The more energetic a particle is, the less it is swayed by magnetic fields, meaning its path should be relatively straight. For Amaterasu to have been bent so severely, the magnetic fields would have to be far stronger than we currently believe, which would itself rewrite textbooks. The more thrilling and unsettling conclusion is that we are seeing evidence of an entirely unknown astrophysical phenomenon. Something hidden within that apparent emptiness, or perhaps something that leaves no other trace, is capable of firing nature's most energetic particles across the universe. Speculation ranges from cosmic strings, hypothetical defects in the fabric of space-time, to the decay of super-heavy dark matter particles that could be clustered in that region. The Amaterasu particle, like its predecessor, is more than just a data point. It is a stark reminder that the universe is brimming with forces and entities we have not yet begun to comprehend, and it challenges us to look deeper into the void to find what is truly there. While the Oh My God and Amaterasu particles challenge our understanding of cosmic accelerators, a series of detections from the most remote continent on Earth hint at something even stranger, a potential crack in the very laws of physics as we know them. High above the vast frozen plains of Antarctica, a sophisticated experiment was launched not to look up at the sky, but to listen down into the ice itself. This was the Antarctic Impulsive Transient Antenna, or ANITA, a balloon-borne instrument designed to drift for weeks on the polar winds. Its mission was to hunt for the ghostliest of cosmic messengers, neutrinos. These nearly massless particles are infamous for their ability to pass through entire planets as if they were empty space. ANITA was built to catch them in a unique way, by detecting the faint radio waves produced when an ultra-high-energy neutrino chanced to smash into an atom within the pristine Antarctic ice sheet. Scientists expected to see a telltale radio pulse from neutrinos coming down from the cosmos above. What they did not expect was to see signals that appeared to be coming up from the ground below. On 4 separate occasions during its multiple flights, ANITA's sensitive detectors picked up something that defied simple explanation. The instrument recorded signals characteristic of an ultra-high-energy particle interaction, but the direction was all wrong. Instead of arriving from the sky, these signals seemed to originate from within the Earth, traveling upward through thousands of kilometers of solid rock and ice before erupting into the atmosphere. The most logical interpretation was that ANITA had detected a specific type of neutrino known as a tau neutrino. When a tau neutrino interacts, it can create a secondary particle called a tau lepton, which, if it decays quickly enough, can produce a radio pulse that travels back up through the ice. This is a known, though very rare, phenomenon. The problem, however, lies in the immense energy of these particular events. The universe is filled with a fog of low-energy radiation, and for a neutrino traveling across cosmic distances, this fog presents a formidable barrier. The higher a neutrino's energy, the more likely it is to interact with matter and radiation along its journey. At the extreme energies detected by ANITA, a neutrino should not be able to travel through a significant fraction of the observable universe without being absorbed. In fact, passing through the entire diameter of our planet, over 12,000 kilometers of dense rock and molten metal, should be absolutely impossible for a neutrino with such energy. It would be like a bullet traveling through a mountain. The mountain always wins. The probability is so vanishingly small that these detections are considered, for all practical purposes, impossible within our standard model of particle physics. This leaves scientists with a tantalizing and profound puzzle. One possibility is that these were not neutrinos at all, but an entirely new type of particle. This hypothetical particle would need to share the neutrino's incredible ability to pass through matter unaffected, but be even more penetrating, able to traverse the entire Earth at energies where known particles would be completely blocked. The search for such a sterile neutrino or other exotic matter is a major frontier in physics. Another, even more mind-bending explanation involves cosmic relics from the Big Bang. Some theories suggest that dark matter, the invisible substance that makes up most of the universe's mass, could be concentrated in a halo around our galaxy. If heavy dark matter particles were to decay or annihilate deep inside the Earth, they could produce the very high energy particles that Anita detected, creating the illusion of something coming from below. In this scenario, Anita wasn't seeing a particle that traveled through the Earth, but one that was born within it. The Anita anomalous events stand as one of the most provocative mysteries in modern astrophysics. They are not just about finding a source in space, but about questioning the fundamental nature of what matter and energy are capable of. While some later analyzers have suggested more mundane explanations involving unusual glacial features or rare background noise, the possibility remains that Anita briefly glimpsed a shadow of physics beyond our current understanding, a physics where particles can perform impossible journeys, pointing to a reality far stranger than we ever imagined. If the "Oh my God" and Amaterasu particles are the universe's exclamation points, a far more subtle but equally profound mystery is written into the very fabric of the cosmic ray rain itself. It's a pattern that emerges not from a single spectacular event, but from the collective whisper of trillions upon trillions of particles. When scientists plot the number of cosmic rays that arrive at Earth against their energy, they don't see a random scatter. Instead, they reveal a remarkably smooth and steady curve, a kind of cosmic power law where for every tenfold increase in energy, the number of particles drops dramatically. This graph, known as the cosmic ray energy spectrum, is the foundational map of high-energy physics in our universe. But like any good map of unexplored territory, it contains a strange and telling feature, a bend, a kink in the curve so distinct that it was given a very simple, evocative name, the knee. This knee occurs at an energy of around 10 to the 15th electron volts. While that number is dwarfed by the staggering energies of the particles we just discussed, it represents a critical turning point. Below this energy, cosmic rays are relatively abundant. You could picture them as a constant, heavy drizzle, but at the knee, the spectrum steepens sharply. The rate of particles with even higher energies falls off a cliff. It's as if the universe has turned down a dial, making the most powerful particles exponentially rarer. For decades, understanding why this bend exists has been a central goal in astrophysics, because it likely holds the key to distinguishing between local and extragalactic cosmic rays. The leading explanation for the knee paints a picture of cosmic rays being trapped and accelerated within the magnetic confines of our own Milky Way galaxy. Imagine our galaxy not as a collection of peaceful stars, but as a vast, dynamic ecosystem crisscrossed by powerful magnetic fields. Within this system, the primary engines for accelerating particles are thought to be the expanding shock waves from supernova remnants. When a massive star explodes, it blasts a shell of material outward at incredible speeds. A proton or atomic nucleus wandering near this shock front can get caught in a magnetic ping-pong game, bouncing back and forth across the shock wave. With each crossing, it gains a little more energy, much like a surfer skillfully riding a wave to gain speed. Over thousands of years, this process can accelerate particles to tremendous energies. The knee, then, may be the natural limit of this galactic accelerator. It could represent the maximum energy at which our galaxy's magnetic fields can effectively contain these particles. Below the knee, the magnetic fields are strong enough to keep the cosmic rays trapped, bouncing around the Milky Way for millions of years, slowly diffusing and filling the entire galactic disk. But once a particle is accelerated beyond this threshold energy, it becomes too powerful to be held by the galaxy's magnetic grip. it effectively achieves escape velocity, breaking free from the Milky Way and streaming out into the intergalactic void. This loss mechanism would naturally cause the number of particles we detect at energies beyond the knee to plummet, creating the steep drop-off we observe. It's a compelling idea that frames our galaxy as a cosmic ray factory with a clearly marked maximum output. However, this is not the only possibility. Another intriguing theory suggests the knee might not be about escape, but about the limits of the acceleration mechanism itself. Perhaps supernova shock waves simply cannot push particles to energies much higher than 10 to the 15th electron volts. The physics of shock acceleration, involving the strength and structure of magnetic fields around the remnant, may have a fundamental ceiling. If this is the case, then the particles we detect beyond the knee must have a completely different origin story, one that lies outside our galaxy entirely. This would mean that the cosmic rays we experience are a mixture of two distinct populations, a steady, abundant drizzle of galactic particles below the knee, and a much rarer but far more energetic shower of intergalactic bullets from beyond. This distinction makes the knee far more than just a curious feature on a graph. It is a fundamental cosmic boundary. It forces us to look up and out to recognize that the highest energy particles, the ones that carry the deepest secrets, are not born in the familiar stellar graveyards of our own galaxy. They are extraterrestrial in the truest sense, arriving from distant galaxies, active black holes, or perhaps even more exotic phenomena. The knee is the shoreline where the tide of our local cosmic ray ocean meets the vast, unexplored sea of the intergalactic medium. By studying this subtle bend with ever more sensitive detectors, we are not just reading a statistic. We are learning about the containment limits of our galactic home and peering into the far more violent and mysterious realms that lie beyond its borders. If the knee of the cosmic ray spectrum represents a shoreline, then the next feature we encounter is a vast, deep ocean. Continuing our journey up the energy scale, we reach a point around 10 to the 18th electron volts where the spectrum performs another surprising about-face. After the steep decline following the knee, the curve unexpectedly flattens out. This feature is known with a touch of anatomical whimsy as the ankle. While it lacks the dramatic, record-shattering energy of a single oh my god particle, the ankle may hold even greater significance for our understanding of the cosmos's large-scale structure. It is here that we cross a fundamental threshold, moving from cosmic rays that are local tourists to those that are intergalactic pilgrims. The flattening of the spectrum is a crucial clue. It suggests that a new population of particles is beginning to dominate the cosmic ray flux. The prevailing hypothesis is that the ankle marks the transition point where the dwindling supply of galactic cosmic rays, those accelerated within the confines of our Milky Way, is finally overtaken by a diffuse background of particles originating from far beyond our galaxy. Think of it as listening to a radio. As you drive away from a local station, its signal grows faint and eventually fades into static. But then a more powerful, distant station broadcasting on a similar frequency begins to come through clearly. The ankle is the point where that new, distant signal becomes the dominant one. These ultra-high-energy particles have traveled for millions, even billions, of years across the unimaginable voids between galaxies to reach us. This long journey, however, is the very thing that makes their existence so challenging to explain. Space is not a perfect vacuum. It is filled with the cosmic microwave background, the cold relic radiation from the Big Bang that permeates every cubic centimeter of the universe. For a proton traveling at these immense energies, this background radiation is no longer a cold mist but a wall of high-energy gamma rays. Due to a bizarre effect of relativity from the proton's point of view, the microwave background photons are massively blue-shifted, appearing as intense high-energy radiation. The proton can interact with these photons to produce new particles, a process that saps its energy significantly over distances of tens of millions of light years. This is known as the Greisen-Zatzepin-Kuzmin, or GZK, cutoff. It acts like a cosmic speed limit for protons, meaning that any particle we detect with energy above the ankle must have originated from a relatively nearby source within our local supercluster of galaxies. Particles from more distant origins should have lost their energy long before arriving at Earth. This presents a monumental challenge for astronomers, finding the celestial accelerators capable of producing such particles within our cosmic neighborhood. The energy required is almost incomprehensible. To overcome the energy losses of intergalactic travel and still arrive with a punch measured in tens of exa-electron volts, the source must be an engine of virtually unimaginable power. Our best candidates are the most extreme phenomena known to astrophysics. Supermassive black holes at the centers of active galaxies can generate jets of plasma stretching for thousands of light years, acting as natural particle accelerators on a gargantuan scale. Cataclysmic events like gamma-ray bursts, which release more energy in a few seconds than our Sun will in its entire 10 billion-year lifetime, are another prime suspect. Even the violent collisions and mergers of entire galaxy clusters have been proposed as potential power sources, yet the hunt for these sources has been frustratingly inconclusive. When we look in the directions from which the highest energy cosmic rays arrive, we often do not see a brilliant active galaxy or a recent gamma-ray burst staring back at us. The particles seem to come from regions of the sky that appear, for all intents and purposes, quiet and unremarkable. This could be due to the gentle but persistent bending of the particles' paths by intergalactic magnetic fields. A proton, being electrically charged, does not travel in a perfectly straight line over millions of light years. These faint magnetic fields can twist its trajectory, much like a lens distorts light, making it incredibly difficult to trace the particle back to its true point of origin. The particle's arrival direction becomes a blurred pointer, pointing not to a single bright source, but to a vast and uncertain region of space. The mystery of the ankle, therefore, forces us to confront the limits of our knowledge on two fronts. It challenges our catalogue of cosmic powerhouses, suggesting that either these engines operate in ways we don't yet understand, or that there are entirely new classes of astronomical objects lurking in the darkness, capable of hurling matter across the universe. Simultaneously, it highlights our profound ignorance about the invisible infrastructure of the cosmos, the strength and structure of the magnetic fields that fill the voids between galaxies. By studying the ankle, we are not just counting particles, we are learning to map the invisible forces that shape the universe and searching for the hidden titans whose power echoes across the light years. As we search for the cosmic engines capable of launching these intergalactic bullets, astronomers have identified a prime suspect lurking relatively close to home, a celestial powerhouse known as Centaurus A. Located a mere 13 million light-years away, which is practically next door in galactic terms, this peculiar object is not like our serene Milky Way. At first glance, it appears as a distorted, dusty lane cutting across a giant elliptical galaxy, the aftermath of a violent galactic collision millions of years in the past. But its true nature is revealed when we observe it across other wavelengths of light. In radio waves, Centaurus A erupts into view, displaying colossal jets of plasma that stretch for over 1 million light-years into intergalactic space, making it one of the largest and most prominent objects in the entire sky. These jets originate from the galaxy's heart, where a supermassive black hole, weighing in at about 55 million times the mass of our Sun, is actively feeding on surrounding gas and dust. It is this frenetic activity that marks Centaurus as a leading candidate for being a natural particle accelerator on an almost unimaginable scale. The process is both violent and elegant. As matter spirals inward toward the black hole's event horizon, it forms a superheated accretion disk, a whirlpool of plasma moving at relativistic speeds. Not all of this material is swallowed. A fraction of it is channeled and focused by intense magnetic fields into two narrow, oppositely directed jets that blast outward from the black hole's poles at nearly the speed of light. Within these jets, charged particles like protons can become trapped in a natural version of a particle accelerator. They surf on shock waves and magnetic fields within the jet, gaining a tremendous amount of energy with each pass. This mechanism is thought to be capable of boosting particles to the ultra-high energy levels we detect here on Earth, potentially explaining the origin of some of the most powerful cosmic rays that reach us. Because of its proximity and its dramatic outbursts, Centaurus represents a unique laboratory for testing our theories about how the universe generates its most energetic particles. The evidence for this connection, while tantalizing, is not a simple case of cause and effect. When researchers from the Pierre Auger Observatory, the world's largest cosmic ray detector, analyzed the arrival directions of the highest energy events, they noticed a curious statistical excess. A number of these particles seem to originate from a broad region of the sky that contains Centaurus A. It wasn't a precise bullseye, but a noticeable clustering that stood out against the otherwise random background of cosmic rays. This was a hugely exciting finding, as it offered one of the first credible hints that we might be pinpointing a specific source for these enigmatic particles. However, this is where the challenge of cosmic detective work truly begins, because a charged particle does not travel through the universe like a photon of light, moving in a perfectly straight line. The space between galaxies is not entirely empty. It is threaded with incredibly weak but pervasive magnetic fields. While these fields are feeble, their influence over a proton traveling millions of light years is profound. A proton carrying a positive electric charge is constantly nudged by these magnetic fields. Its path becomes a long, slow, winding curve, a journey akin to a pinball bouncing between invisible bumpers. By the time the particle finally arrives at Earth, its trajectory may point back to a region of the sky that is far removed from its actual source. This magnetic deflection blurs the celestial map, making it extraordinarily difficult to trace a cosmic ray back to its point of origin with any precision. The clustering of events around the direction of Centaurus is suggestive, but it could also be a coincidence, with the particles having been bent from other, more distant sources that just happen to lie in a similar part of the sky. This uncertainty fuels a vibrant scientific debate. Some models suggest that if the magnetic fields are on the stronger end of what we think is possible, the connection to Centaurus could be entirely illusory. Other models, however, show that the observed clustering is consistent with what we might expect if Centaurus were indeed the source, especially when we consider that the highest energy particles, which are the most resistant to magnetic deflection, show the strongest correlation. The search for a smoking gun continues, with astronomers looking for other telltale signatures, such as neutrinos or gamma rays, that will be produced alongside cosmic rays in the galaxy's powerful jets. A simultaneous detection of a cosmic ray and a neutrino from the same patch of sky containing Centaurus would be considered landmark evidence, as neutrinos, being neutral, travel in perfectly straight lines and would point directly back to their source. For now, Centaurus remains our best and most compelling candidate, a nearby giant whose turbulent heart may be constantly firing invisible messengers across the cosmos. Its signal just clear enough to tease us with the possibility of an answer, yet still shrouded in the fundamental uncertainty of the universe's invisible magnetic tapestry. This brings us to one of the most profound predictions in all of astrophysics, a theoretical wall that cosmic rays should not be able to breach. In the 1960s, three physicists, Kenneth Greisen, Georgy Zatsepin, and Vadim Kuzmin, independently calculated a fundamental limit to how far the most energetic particles can travel through the universe. Their work defined what is now known as the GZK cutoff. The principle is based on a simple but powerful idea: space is not empty. It is filled with the faint, cold glow of the cosmic microwave background, the afterglow of the Big Bang. For you and me, this background radiation is a whisper, a relic of a time long past. But for a proton traveling at almost the speed of light, this whisper becomes a deafening roar. Due to the bizarre effects of special relativity, from the perspective of an ultra-high-energy proton, the low-energy microwave photons are massively blue-shifted, appearing as a barrage of high-energy gamma rays. When such a proton smashes into one of these photons, the collision can create new particles, most notably a pion. This process saps the proton's energy, effectively causing it to slow down over cosmic distances. The GZK cutoff, therefore, is not a hard barrier but a statistical one. It predicts that the journey for a proton with an energy above about 6 times 10 to the 19th electron volts should be brutally short on an intergalactic scale. After traveling roughly 160 million light-years, such a particle would have lost so much energy that it would fall below this threshold. This creates a cosmic horizon, a sphere around Earth beyond which the highest energy cosmic rays cannot reach us. Any particle we detect with energy beyond the GZK limit must, according to the theory, have originated from within our local supercluster of galaxies. The enigma deepened when experiments like the Pierre Auger Observatory and the telescope array began collecting data. They did not find a sharp cutoff where the cosmic ray spectrum abruptly ended. Instead, they observed a suppression, a gradual steepening of the curve around the predicted energy. This was a triumph for the standard model of particle physics. The GZK effect was real, and it was shaping the universe we observe. But then came the outliers. Sprinkled among the data were those legendary particles, the Oh My God and Amaterasu events, with energies far exceeding the GZK limit. Their existence poses a direct challenge. If the GZK process is as effective as we believe, how do these particles make it to Earth without being completely drained of their energy? The most straightforward explanation is that their sources are exceptionally close by, cosmically speaking. They must be born within our local galactic neighborhood, well within the 160 million light-year safety zone, where the journey is so short that there simply isn't enough time for significant energy loss to occur. This turns the mystery into a frantic search for a nearby cosmic accelerator of unimaginable power. This search, however, has been like looking for a ghost. When we trace the arrival directions of these super GZK particles, we often find them pointing towards empty voids, like in the case of the Amaterasu particle, or towards regions devoid of any known astrophysical powerhouses capable of such feats. There are no recent supernova remnants, active galactic nuclei, or gamma-ray bursts in the immediate vicinity that stand out as obvious culprits. This absence forces us to consider the other, far more thrilling possibility, that our understanding of particle physics at these extreme energies is incomplete. Perhaps the GZK process doesn't work exactly as we think under conditions we cannot replicate in our laboratories. There could be exotic particles involved that do not interact with the cosmic microwave background in the same way as protons. Some theories even entertain the idea of Lorentz invariance violation, a concept where the very rules of special relativity which underpin the GZK calculation might break down at energies this high. This would be a revolution in physics, suggesting that the fundamental symmetry of spacetime itself is not absolute. The GZK cutoff mystery, therefore, is a double-edged sword. Its observed suppression confirms a key prediction of our standard models, painting a consistent picture of a universe filled with relic radiation. Yet, the defiant particles that punch through this ceiling are the true messengers of the unknown. They are either pointing to hidden monsters lurking in the dark of our local cosmic backyard, or they are carrying evidence of new physics that operates at energies trillions of times greater than anything we can create on Earth. Every detection of a particle beyond the GZK limit is a direct probe into the most extreme regimes of nature, challenging us to either find the celestial engines we have missed or to rewrite the textbooks on the fundamental laws that govern reality. But if we are searching for an engine powerful enough to launch the most extreme cosmic rays, we must look to the most violent explosions known to exist. For a few fleeting seconds, a gamma-ray burst can outshine every other source of light in the universe combined. These are not mere stellar flares, they are catastrophic events, the death throes of the most massive stars or the collisions of ultra-dense stellar remnants. In terms of raw, focused energy, they are unrivaled, surpassed only by the Big Bang itself. It stands to reason that such titanic convulsions could also be the ultimate cosmic ray accelerators, forging particles with energies that dwarf anything our own galaxy could possibly produce. The physics within a gamma-ray burst is almost incomprehensibly extreme. As a massive star collapses into a black hole or two neutron stars spiral together and merge, they unleash twin jets of plasma moving at over 99.99% of the speed of light. Within these narrow, focused beams, a frenzy of activity takes place. Two primary mechanisms are theorized to act as nature's particle accelerators. The first involves internal shocks. Because the jet is not emitted as a smooth flow but in violent, erratic pulses, faster-moving material can slam into slower-moving material from behind. These collisions create immense shock waves that ripple through the jet, and charged particles like protons can get caught in these magnetic turbulence, bouncing back and forth across the shock front and gaining a tremendous boost in energy with each pass. The second mechanism is magnetic reconnection, a process where the powerful, tangled magnetic fields within the jet suddenly snap and reconfigure, releasing a colossal amount of stored energy directly into accelerating nearby particles. In this environment of pure chaos and unimaginable power, protons could be accelerated to the ultra-high energies we detect, becoming the very cosmic rays that puzzle us so deeply. The elegance of this hypothesis is that it neatly solves the energy problem. The total energy budget of a gamma-ray burst is more than sufficient to account for even the oh my god particle. Furthermore, these events are relatively rare on a human timescale but common across the cosmos, happening several times a day somewhere in the observable universe. This could explain why we detect these ultra-high-energy cosmic rays so infrequently. We are essentially sampling the aftermath of the most powerful explosions across millions of galaxies. However, connecting a specific cosmic ray to a specific gamma-ray burst presents a detective challenge of epic proportions. The light from a gamma-ray burst is brilliant but fleeting, lasting from a few milliseconds to a few minutes. Our satellites, like the Swift and Fermi telescopes, are excellent at spotting these flashes and quickly pinpointing their location in the sky. But a cosmic ray is a different kind of messenger. A proton, being electrically charged, does not travel in a straight line. As we've discussed, it is bent and deflected by the magnetic fields that fill intergalactic space. Its journey from the burst to Earth is a long, winding, and slow meander compared to the photons that race directly to us at the speed of light. This means that by the time a cosmic ray born in a gamma-ray burst finally arrives at our detectors, the light from the explosion that created it faded away millions of years ago. The burst itself is a distant, silent memory. We are left with the bullet, but the gun has long since vanished. This time delay turns the search for evidence into a statistical game. Instead of looking for a one-to-one match, scientists search for correlations. They might analyze the arrival directions of many ultra-high-energy cosmic rays to see if they cluster in a way that aligns with the known distribution of galaxies where gamma-ray bursts are likely to occur. Another promising avenue involves searching for a different, neutral messenger, the neutrino. The same violent processes that accelerate protons should also produce high-energy neutrinos. Unlike protons, neutrinos are not deflected by magnetic fields, and they travel at nearly the speed of light. If we could ever detect a high-energy neutrino at the same time as a gamma-ray burst, it would be a smoking gun, confirming that these explosions are indeed producing high-energy particles. While a few tantalizing coincidences have been noted, that definitive, simultaneous detection remains the holy grail of this field. The hypothesis that gamma-ray bursts are cosmic ray factories is powerfully compelling, but for now, the evidence remains just out of reach, a whisper of a connection across the vast gulf of space and time. While individual particles like the Amaterasu event point towards the void, a completely different kind of clue emerges when we step back and look at the big picture, at the collective arrival directions of many ultra-high-energy cosmic rays. This is where the work of the Pierre Auger Observatory becomes so vital. Located on a vast, high plain in Argentina, Auger is not a single telescope but an enormous array, a network of 1,600 water tanks spread over 3,000 square kilometers, an area roughly the size of Rhode Island, complemented by a series of fluorescence detectors that scan the night sky. This immense scale is necessary because the most energetic cosmic rays are so incredibly rare. Auger's purpose is to catch as many of these rare events as possible, and crucially, to map where on the celestial sphere they seem to be coming from. After years of patient data collection, the collaboration announced a finding that sent ripples through the astrophysics community, a hotspot. Not a single precise point, but a broad, statistically significant excess of these particles arriving from a general direction in the sky, an area about 40 degrees across near the constellation Centaurus. This clustering is a profound piece of evidence. Imagine you are standing in a field during a very light, sporadic rain, where only a few drops fall each hour. If you meticulously recorded where each drop hit for years, you would expect them to be randomly scattered across the ground. But if you started to see a noticeable pattern, if significantly more drops consistently landed within one particular patch of grass, even a large one, you would suspect that perhaps the rain wasn't entirely random. Maybe there was a subtle, persistent breeze channeling the drops from a specific direction. The Auger hotspot is that pattern. It suggests that there is something in that part of the sky, something within our local cosmic neighborhood, that is a prolific source of these incredible particles. It offers the tantalizing possibility that we are not just dealing with random, isolated events, but that we can actually begin to create a map of the universe's most powerful accelerators. The immediate and most compelling suspect in that region of space is, as we discussed, Centaurus A. This nearby active galaxy with its colossal jets is a prime candidate capable of such acceleration. The hotspot's location aligns broadly with its position, making it the most obvious source for the observed clustering. However, the plot thickens considerably when we ask a critical question. Is this hotspot pointing to a single, monstrous engine like Centaurus A, or is it the combined signal of many sources? The size of the hotspot is key here. It's not a sharp, pinpoint location. This blurriness is almost certainly caused by the same cosmic challenge we've encountered before, magnetic deflection. As ultra-high-energy protons travel through the magnetized plasma that fills the space between galaxies, their paths are gently curved. The weaker the particle's energy, the more it gets bent. So, by the time a family of particles from a single source arrives at Earth, they will have fanned out, appearing to come from a wide patch of sky rather than a single point. The 40-degree width of the Auger hotspot could therefore be consistent with the signal from one dominant source, like Centaurus A, smeared across the heavens by these invisible magnetic lenses. But another, equally intriguing possibility is that we are not looking at one source, but at a dense concentration of cosmic powerhouses. The direction of the Auger hotspot points towards the heart of our local supercluster of galaxies, a vast structure known as Laniakea. This is the galactic metropolis to which our Milky Way belongs, a gravitational watershed containing over 100,000 galaxies. Within this immense congregation, there are many potential accelerators, other active galactic nuclei, starburst galaxies, and perhaps even larger-scale structures like the powerful shock waves generated by colliding galaxy clusters. The hotspot might not be a signal from a single lighthouse, but the combined glow of an entire city of cosmic engines, their individual signals overlapping to create a bright patch on our cosmic ray map. This would mean that the ultra-high-energy universe is not dominated by a few rare monsters, but is instead illuminated by a relatively nearby population of sources, all contributing to the rain of particles we detect. This ambiguity is the core of the mystery. Is the signal a focused beam that has been diffused, or a diffuse glow that appears focused? Distinguishing between these scenarios is one of the greatest challenges in the field. The answer hinges on understanding the strength and structure of the intergalactic magnetic fields, which is itself a major unsolved problem in cosmology. If the fields are stronger than we think, then the hotspot could easily be the smeared-out signal of Centaurus A. If the fields are weaker, then the particles would have traveled on straighter paths, and the large size of the hotspot would indeed suggest multiple sources. Future observations with even larger detectors will be crucial. By collecting more events, scientists hope to see if the clustering becomes sharper at the very highest energies, where magnetic bending is minimal. A sharper peak would strongly point to a single, dominant source. For now, the Auger hotspot remains a powerful and suggestive clue, a testament to the fact that even when the universe seems to be giving us a clear signal, it is still speaking in a code that requires all our ingenuity to decipher. It confirms that the sources of these particles are not randomly distributed across the sky, but are concentrated in the same cosmic structures that define the large-scale architecture of our universe, bringing us one step closer to identifying the titans that shape the invisible high-energy cosmos. The recurring puzzle of the Amaterasu particle is far from an isolated case. It is part of a disturbing pattern that challenges our most basic assumptions about where cosmic violence originates. Time and again, when researchers trace the paths of the most energetic cosmic rays back to their supposed sources, they are met with a profound emptiness. These trajectories point not towards the brilliant lights of active galaxies or the chaotic hearts of galaxy clusters, but into the vast, desolate expanses known as cosmic voids. These are the emptiest places in the universe, regions spanning hundreds of millions of light years where galaxies are few and far between, and the density of matter is a tiny fraction of the cosmic average. The very idea that such emptiness could produce the most energetic particles in existence is a contradiction that strikes at the core of modern astrophysics. Our entire understanding of particle acceleration is built upon environments of extreme density and energy. We look to supernova remnants where shock waves expand through dense stellar material. We point to the cores of active galaxies where vast amounts of matter are compressed into an accretion disk around a supermassive black hole. These are places of immense gravitational and magnetic power, natural factories for forging high-energy projectiles. A cosmic void, by its very definition, lacks all of this. It is a near vacuum, a place where the raw materials for such cosmic engines simply do not exist. It would be like expecting a volcanic eruption to occur in the middle of the deep ocean floor, far from any tectonic plate boundary. The environment is fundamentally wrong for the phenomenon we are observing. This inconsistency forces us to confront two equally radical possibilities. Either our methods for tracing these particles are deeply flawed, or our understanding of what can happen in the void is completely inadequate. One of the most intriguing solutions lies in the nature of the invisible universe. While these voids appear empty of luminous matter, they may not be empty of the universe's dominant component, dark matter. This mysterious substance, which makes up about 85% of all matter, does not interact with light, but it does exert a powerful gravitational pull. It is possible that these voids are actually filled with vast, diffuse halos of dark matter. If certain types of dark matter particles are extremely heavy and unstable, they could spontaneously decay, annihilating with each other and releasing their immense rest mass energy in a burst of standard model particles, including protons accelerated to ultra-high energies. In this scenario, the void is not empty at all. It is a reservoir of latent power. The cosmic ray we detect would not be a bullet fired from a distant cannon, but the final death cry of a primordial particle that has been waiting to decay since the earliest moments of the universe. The source would be everywhere and nowhere within the void, explaining why we see no pinpoint origin. An even more exotic possibility involves defects in the very fabric of spacetime itself. According to some theories of the early universe, as it expanded and cooled from the Big Bang, it may have undergone phase transitions similar to water freezing into ice. And just as ice can form cracks and fissures, the fabric of spacetime could have developed one-dimensional flaws called cosmic strings. These are not strings in the everyday sense, but incredibly thin, ultra-dense filaments of energy thinner than a proton but stretching across the entire universe. They would be quantum objects of cosmic scale, possessing immense tension. If two segments of a string were to cross or a loop were to snap, the event would release a catastrophic amount of energy, potentially creating ultra-high-energy cosmic rays. Because cosmic strings are topological defects, they would not be tied to galaxies or clusters. They could easily reside in the great voids, their immense energy hidden in plain sight, only betraying their presence when they momentarily snap and send a particle on a multi-million-year journey to our detectors. Of course, we must also consider the simpler explanation that we are being fooled by magnetism. The deflection of a proton's path by intergalactic magnetic fields remains the most conservative solution to the void origin problem. Perhaps the particle did come from a brilliant, active galaxy, but its path was bent so severely during its long journey that its apparent origin in the void is just a cosmic illusion. The challenge with this idea is that the higher a particle's energy, the more resistant it is to magnetic bending. For a particle with the energy of Amaterasu to be deflected enough to appear to come from a void, the magnetic fields in intergalactic space would have to be significantly stronger and more structured than our current models allow. This would itself be a major discovery, revealing that the empty spaces between galaxies are threaded with a powerful, invisible infrastructure that we have yet to map. The void origin problem, therefore, is a gateway to a deeper mystery. It forces us to question not just what the sources of cosmic rays are, but to investigate the invisible landscape through which they travel. A landscape that may be far more complex and energetic than the map of visible light reveals. While the hunt for cosmic monsters capable of launching universe-spanning projectiles captures the imagination, a far more subtle and personal drama unfolds much closer to home, orchestrated by our own life-giving star. The sun may seem like a steady beacon, but it is a dynamic and temperamental sphere, and its activity creates a protective bubble that directly shapes the invisible rain of cosmic rays that reaches our planet. This phenomenon is known as the solar modulation effect, and it reveals that the story of cosmic rays is not just about distant cataclysms, but also about an ongoing, rhythmic dance between the sun and the galaxy. At the heart of this interaction is the heliosphere, a vast magnetic bubble blown into the interstellar medium by the solar wind. This wind is a constant stream of charged particles, protons and electrons flowing outward from the sun at speeds of millions of kilometers per hour. The heliosphere extends far beyond the orbit of Pluto, acting as a protective shield for our entire solar system. When galactic cosmic rays, which are also charged particles, approach from interstellar space, they must fight their way through this turbulent, magnetized barrier. Think of it as trying to swim upstream against a powerful, chaotic river. The solar wind and its embedded magnetic field act as a deterrent, scattering and decelerating the incoming cosmic rays, reducing their intensity before they can penetrate into the inner solar system. This creates a direct and inverse relationship with the sun's 11-year activity cycle. During solar maximum, when the sun is covered in numerous sunspots and is unleashing frequent solar flares and coronal mass ejections, the solar wind is stronger and more turbulent. This enhanced activity makes the heliosphere a more effective shield, leading to a significant decrease in the number of galactic cosmic rays that manage to reach Earth. Conversely, during solar minimum, when the sun is comparatively calm, the solar wind weakens. The heliospheric barrier becomes more porous, allowing a greater flux of cosmic rays to pour into our cosmic neighborhood. This modulation is most effective for cosmic rays at the lower end of the energy spectrum. The most energetic particles, like the oh my god particle, possess so much momentum that they punch through the heliosphere virtually unaffected, like a cannonball ignoring a gentle breeze. But for the vast majority of cosmic rays, the sun acts as a variable dial, turning the cosmic ray flux up and down in a predictable, decade-long rhythm. This dynamic interaction is not just a scientific curiosity. It has left a permanent record of solar activity etched into our own planet. When a galactic cosmic ray, which is typically a high-energy atomic nucleus, slams into the upper atmosphere, it shatters nitrogen and oxygen atoms, creating a cascade of secondary particles. Among these secondary particles are rare isotopes like carbon-14 and beryllium-10. These isotopes are then incorporated into the Earth's biosphere and geology. Carbon-14 is absorbed by plants during photosynthesis and becomes part of the annual growth rings of trees. Beryllium-10 falls to the ground and is preserved in layers of ice in glaciers and polar ice caps. The rate at which these isotopes are produced is directly proportional to the intensity of the cosmic ray flux bombarding our atmosphere. Therefore, by analyzing the concentration of carbon-14 in ancient tree rings or beryllium-10 in deep ice cores, scientists can effectively look back in time thousands of years to reconstruct a history of cosmic ray intensity. And since that intensity is modulated by the sun, these natural archives become a proxy record for solar activity. A period of high carbon-14 or beryllium-10 concentration in a specific tree ring or ice layer indicates a time when the cosmic ray flux was high, which corresponds to a period of a weak solar wind and a quiet sun. Conversely, a drop in these isotopes points to a time of heightened solar activity. This has allowed researchers to identify grand solar minima in the past, like the famed Maunder minimum between the 1650s and 1750s, when sunspots virtually disappeared and the Earth experienced a little ice age. The cosmic ray record confirms that during this decades-long period, our sun was exceptionally quiet, allowing more galactic particles to reach Earth and leaving their mark in the ice and wood. The solar modulation effect beautifully ties together the cosmic and the terrestrial. It demonstrates that our local star is not an isolated entity but an active participant in the galactic environment, constantly interacting with the broader galaxy. This understanding is also crucial for practical applications, such as assessing radiation doses for astronauts and airline crews who receive higher exposures during solar minimum. By studying this rhythmic interplay, we learn that the story of cosmic rays is not solely written in the distant voids or by colossal explosions, but is also intimately woven into the very fabric of our solar system's climate and history, revealing a connection between the sun's temper and the secrets preserved in ancient ice and wood. But beyond leaving a mark in ancient ice and tree rings, cosmic rays may be interacting with our planet in a far more direct and dynamic way, influencing the very fabric of our atmosphere and potentially our climate. This brings us to a fascinating and deeply controversial hypothesis that links the most energetic events in the galaxy to something as everyday as a cloudy sky. The idea is that cosmic rays could play a significant role in seeding cloud formation on Earth, a concept that, if proven true, would connect the grandest cosmic processes to the delicate balance of our own planetary environment. The proposed mechanism begins with a single, high-energy particle from deep space slamming into the upper atmosphere. As it collides with an air molecule, it creates a cascade of secondary particles, and among the most important for this theory are free electrons. This process, known as ionization, creates charged pathways in the air. The hypothesis suggests that these ions can act as microscopic anchors, making it easier for certain trace gases, like sulfuric acid or water vapor, to cluster together and form stable, tiny particles called aerosols. In the complex ballet of atmospheric science, these aerosols are crucial. They serve as cloud condensation nuclei, the essential seeds upon which water vapor can condense to form the droplets that make up a cloud. Without these nuclei, even in humid air, clouds would be much harder to form. The theory posits that by increasing the number of these seeds, an intense flux of cosmic rays could lead to the formation of more clouds, particularly low-level clouds that tend to reflect sunlight back into space, thus having a cooling effect on the planet. The evidence for this connection often points to a notable correlation observed over the Sun's 11-year cycle. As we discussed during solar maximum, the Sun's heightened magnetic activity deflects more galactic cosmic rays, reducing the number that reach Earth. Satellite data over several decades has shown that during these periods of high solar activity and low cosmic ray flux, the Earth's cloud cover, specifically low-altitude clouds over the oceans, appears to decrease slightly. Conversely, when the Sun is quiet during solar minimum and cosmic ray intensity increases, global cloud cover seems to increase as well. This correlation is compelling to some researchers, suggesting a possible causal link where cosmic rays act as a variable dial for cloud formation, with the Sun acting as the intermediary. However, this is where the scientific debate becomes intense. Correlation does not equal causation, and the climate system is an incredibly complex web of interactions. Many atmospheric physicists argue that the observed changes in cloud cover are too small to be significant, and that they could be explained by other, more direct effects of solar variability, such as small changes in the Sun's total energy output or in ultraviolet radiation, which can affect atmospheric circulation patterns. The central challenge lies in proving the mechanism in the real world. While laboratory experiments have shown that ionization can indeed enhance the formation of tiny aerosol clusters under controlled conditions, scaling this up to the vast, messy, and dynamic environment of Earth's entire atmosphere is a monumental task. The atmosphere already has an abundance of cloud condensation nuclei from other sources, like sea spray, dust, and human-made pollution. The critical question is whether the additional nuclei created by cosmic rays are numerous and stable enough to compete with these other sources and genuinely alter cloud properties on a global scale. The implications of this debate are profound. If the cosmic ray cloud connection is a major driver of climate, it would suggest that long-term changes in our galaxy's cosmic ray flux, caused by factors like the solar system's journey through the Milky Way's spiral arms, could have influenced Earth's climate over geological timescales, potentially triggering or ending ice ages. It would add a powerful external forcing factor to our climate models. Yet, the overwhelming scientific consensus, as reflected in reports by the Intergovernmental Panel on Climate Change, is that the warming observed over the past century is primarily driven by human emissions of greenhouse gases. While cosmic rays may play a minor modulating role, the evidence does not support them being a dominant factor in current climate change. The research continues, with scientists using sophisticated models and seeking clearer signals in the data, as this intriguing hypothesis stands at the crossroads of astrophysics and climatology, reminding us that our planet is not an isolated system but a participant in a much larger cosmic environment. While we have been exploring the immense power of atomic nuclei hurtling across the cosmos, a parallel and equally profound mystery unfolds on a much smaller scale, involving the universe's most elusive and enigmatic form of matter. As cosmic rays travel through space, they don't just consist of ordinary protons and heavier atomic nuclei. mixed into this high-energy soup are particles of antimatter. The very existence of these antimatter particles in cosmic rays presents a fascinating puzzle, one that has intensified with recent discoveries pointing to an unexpected and unexplained excess that might be a whisper from the dark side of the universe. To understand why this is so surprising, we need to recall a fundamental asymmetry of our cosmos. During the Big Bang, matter and antimatter should have been created in equal amounts, yet for some reason that remains one of physics' greatest unsolved problems. Almost all the antimatter vanished, leaving behind the matter-dominated universe we inhabit today. Antimatter is incredibly rare. When a particle of matter meets its antimatter counterpart, an electron meeting a positron or a proton meeting an antiproton, they annihilate each other in a flash of pure energy. Therefore, finding antimatter in space is a significant event. The antiprotons we detect in cosmic rays are generally understood to be secondary particles. They are not blasted out directly from cosmic accelerators, but are created when high-energy primary cosmic rays, like protons, collide with the sparse atoms of the interstellar medium. These collisions are so violent that they can convert energy into mass, creating matter-antimatter particle pairs. The number of antiprotons we see aligns reasonably well with these predictions, providing a reassuring consistency with our standard models of cosmic ray propagation. The mystery truly deepens when we turn our attention to a different antimatter particle, the positron, which is the antimatter twin of the electron. For years, our understanding followed a similar logic. Positrons should also be secondary products created in those same collisions between cosmic rays and interstellar gas. Their numbers should steadily decrease as their energy increases, following a predictable, smooth curve. But this is not what advanced experiments have found. Instruments like the Payload for Antimatter Exploration and Light Nuclei Astrophysics, or PAMELA, satellite, and its immensely sophisticated successor, the Alpha Magnetic Spectrometer, or AMS-02, mounted on the International Space Station, have revealed something extraordinary. Starting at energies around 10 giga-electronvolts, the positron fraction, the ratio of positrons to the total number of electrons and positrons, begins to rise. It does not continue to fall as expected. Instead, it climbs steadily, forming a distinct and unexpected peak before eventually tapering off at very high energies. This is the famous positron excess, a clear and robust signal that something is adding an extra population of high-energy positrons to the cosmic mix, a signal that conventional astrophysics struggles to explain. So, what could be producing this surplus of antimatter? Scientists have put forward two primary categories of explanation, one pointing to known but extreme astrophysical objects, and the other venturing into the realm of the unknown. The leading conventional candidate is the pulsar, the rapidly spinning, ultra-dense remnant of a supernova explosion. These cosmic lighthouses generate powerful, swirling magnetic fields that can accelerate particles to tremendous energies. As these particles interact in the magnetosphere surrounding the pulsar, they could produce electron-positron pairs in vast quantities, which would then stream out into the galaxy. Several nearby pulsars, such as Geminga and its companion PSRB 0656+14, are considered strong contenders, as their estimated age and distance could plausibly account for the observed positron flux we measure today. The positrons would have had just enough time to travel from the pulsar to Earth, their energy matching the mysterious peak in the data. However, the pulsar explanation, while compelling, is not without its challenges. To match the precise shape of the positron spectrum measured by AMS-02, the models require very specific conditions regarding how the particles escape the pulsar's environment and propagate through the tangled magnetic fields of the galaxy. The data shows a remarkably smooth and steady rise, followed by a sharp cutoff at the highest energies, a pattern that is difficult for some pulsar models to reproduce perfectly. This lingering uncertainty is what keeps the door wide open for a far more thrilling possibility: that the positron excess is not an astrophysical signal at all, but a direct signature of dark matter. This is where the mystery connects to one of the greatest unsolved problems in all of science. Dark matter, the invisible substance that makes up about 85% of the matter in the universe, has so far revealed itself only through its gravitational pull. We have no idea what it is made of. One of the leading theoretical candidates is a class of particles known as weakly interacting massive particles, or WIMP. If these particles exist, they could occasionally collide and annihilate each other, or perhaps slowly decay over astronomical timescales. Either process would convert their mass into energy, producing a cascade of standard model particles, including critically electron-positron pairs. The energy spectrum of these positrons would depend directly on the mass of the dark matter particle. The sharp cutoff observed at the highest energies by MS02 could therefore be a direct measurement of the dark matter particle's mass, as there simply wouldn't be enough energy available to create positrons beyond that point. The hunt is now a fierce competition between these two visions of the cosmos. Is the positron excess a testament to the incredible power of pulsars, or is it the first faint glow from the annihilation of the universe's dominant but hidden component? To distinguish between them, astronomers are looking for additional clues. A dark matter signal should be uniform across the sky, as the dark matter halo of our galaxy is believed to be smooth and spherical. A signal from a nearby pulsar, however, might show a slight anisotropy, a directional preference pointing back to its source. As detectors like MS02 continue to collect more data, and as we study other potential byproducts of dark matter annihilation, such as antiprotons or gamma rays, we may finally get a decisive answer. The mystery of the antimatter cosmic rays is thus a beautiful example of how a subtle anomaly in a particle's journey can open a window into the deepest secrets of the cosmos, forcing us to choose between spectacular stellar corpses and the invisible particles that shape the universe itself. While we often look far beyond our galaxy for cosmic mysteries, one of the most dramatic structures ever discovered was hiding in plain sight, emanating from the very heart of our own Milky Way. In 2010, scientists analyzing data from the Fermi Gamma Ray Space Telescope made a stunning find. They revealed two colossal, hourglass-shaped lobes of intense gamma ray emission, ballooning out from the galactic center above and below the plane of the Milky Way. Each of these structures, now known as the Fermi bubbles, stretches an astonishing 25,000 light-years from end to end, meaning this entire formation is larger than the visible disk of our galaxy itself. They are a permanent, faintly glowing monument to some cataclysmic event in our galaxy's past, and they may hold the key to understanding a significant source of the cosmic rays that permeate our local environment. The origin of these gigantic bubbles is a subject of intense debate, but the leading theory points to a violent outburst from the supermassive black hole that resides at the galactic center, a behemoth named Sagittarius, a star. While this black hole is relatively quiet today, it may not have always been so dormant. The prevailing idea is that several million years ago, Sagittarius, a star, experienced a frenzied period of activity, gorging itself on a vast cloud of gas or perhaps even a star that ventured too close. As immense amounts of matter spiraled into the black hole, a portion of that material was channeled by powerful magnetic fields and blasted away from the poles at near light speed, creating two opposing jets of relativistic plasma. These jets would have punched through the galactic disk, inflating the enormous bubbles we see today. The gamma-ray glow we detect is thought to come from within this bubble structure, where the trapped plasma interacts with the galaxy's own light and magnetic fields, causing electrons to accelerate and radiate at the highest energies. This ancient eruption would have been a perfect engine for accelerating cosmic rays. The shock waves generated by the jets plowing into the surrounding galactic halo would have acted as a colossal natural particle accelerator, far more powerful than any supernova remnant within the galaxy. Protons and other atomic nuclei caught in these turbulent fronts could have been boosted to tremendous energies. The key evidence supporting this idea comes from a specific type of cosmic ray, the positron, the antimatter counterpart of the electron. Experiments have detected an unexpected surplus of high-energy positrons arriving at Earth, and one compelling explanation is that they are produced when cosmic ray protons, accelerated within the Fermi bubbles, collide with ordinary atoms in the interstellar medium. These collisions create showers of particles, including electron-positron pairs, which could account for the mysterious antimatter flux we measure. Studying the cosmic rays potentially linked to the Fermi bubbles is like performing an archaeological dig into the history of our galaxy's core. The bubbles are not a static structure, they are a fossil record of a single titanic event. By analyzing the energy and composition of cosmic rays that might have originated from this eruption, scientists can work backwards to understand the nature and power of the outburst that created them. The chemical signature of these particles, the specific mix of elements like carbon, oxygen, and iron, could reveal what kind of material was consumed by the black hole. The energy spectrum of the particles can tell us about the strength of the shock waves that accelerated them. This turns cosmic rays into direct messengers from a long-vanished cataclysm, allowing us to reconstruct a chapter of the Milky Way's history that would otherwise be completely lost to time. However, a fascinating alternative theory suggests the bubbles might not be the work of the central black hole alone. Another potential sculptor could be a period of intense star formation near the galactic center. If a wave of massive stars were born and died in quick succession, their collective stellar winds and supernova explosions could have blown a giant pressurized bubble of hot gas outwards. This starburst model would also produce shock waves capable of accelerating cosmic rays, though the energy signature might differ from a black hole jet. Distinguishing between these two scenarios is an active area of research. Scientists are meticulously mapping the faint edges of the bubbles and searching for subtle features in the gamma-ray and X-ray data that might betray the true culprit. The Fermi bubbles, therefore, stand as a monumental reminder that our own galaxy has not been a peaceful island in the cosmos. It too has experienced its own violent eruptions, and the cosmic rays we detect today may be the final, fading echoes of that forgotten tempest. Yet for all its elegance, this long-standing paradigm faces a critical and persistent challenge, finding the smoking gun. We can see the accelerated electrons clearly. Their synchrotron radiation paints the beautiful, filamentary shells of supernova remnants in X-ray images. But an electron is a lightweight particle, easy to accelerate to high speeds. The real workhorses of the galactic cosmic ray population are protons, which are nearly 2,000 times heavier. Proving definitively that these proton bullets are being forged in the same shocks has been surprisingly difficult. The issue is that a proton, after it is accelerated, does not immediately radiate away its energy like an electron does. It becomes a silent, invisible bullet, carrying its immense kinetic energy across the galaxy until it finally collides with something, often millions of years later and light years away from its source. How do you prove a specific supernova remnant is a proton factory when the products leave no return address? The key to solving this puzzle lies in a specific chain of events that should occur right at the shock front. When an accelerated proton racing away from the remnant collides with a slow-moving proton from the surrounding interstellar gas, the interaction can produce a neutral pion. This subatomic particle is incredibly short-lived, decaying in a mere fraction of a nanosecond into two high-energy gamma-ray photons. This gamma-ray emission is the unique fingerprint we need. Unlike the broad, continuous glow of synchrotron radiation from electrons, the gamma-ray signal from pion decay has a very distinctive energy signature. Detecting this signature in the light coming from a supernova remnant would be the direct, incontrovertible evidence that protons are being accelerated there to cosmic ray energies. The hunt for this pion decay signal has been a major driver for the latest generation of gamma-ray telescopes, both on the ground and in space, and the results have been tremendously encouraging. Remnants like Tycho's supernova, the 1,000-year-old remnant from the explosion witnessed in 1572, show a clear excess of high-energy gamma rays that aligns beautifully with the predictions of the theory. The gamma-ray emission is spatially correlated with the expanding shock wave, and its spectrum is difficult to explain without invoking proton collisions. Similar evidence has been found for other prominent remnants, including the spectacular Cassiopeia A, the dusty wreckage of a star that exploded about 350 years ago. These observations have turned the supernova remnant paradigm from a compelling idea into a strongly supported, observationally grounded theory. We are now increasingly confident that these stellar cataclysms are indeed the primary furnaces where the bulk of the cosmic rays filling our galaxy are born. However, even with this success, lingering questions remain that prevent us from declaring the case completely closed. While the gamma-ray data is highly suggestive, some astrophysicists point out that alternative, more complex models involving only ultra-energetic electrons could, under very specific conditions, potentially mimic the pion decay signature. To eliminate all doubt, scientists are now pursuing multi-messenger observations. The idea is to look for other particles that will be created alongside the protons in the acceleration process. When protons collide to create pions, they also produce neutrinos. These ghostly particles, unlike gamma rays, travel in perfectly straight lines unaffected by magnetic fields. The detection of a high-energy neutrino coming directly from a known supernova remnant like Tycho or Cassiopeia would be the ultimate confirmation, a direct telegram from the heart of the cosmic ray accelerator itself. Experiments like IceCube in Antarctica are constantly scanning the skies for just such a signal. The supernova remnant paradigm has brought us to the brink of a full understanding of our galaxy's cosmic ray origin, but the final, definitive proof may be carried not by a photon of light, but by a nearly massless neutrino from a star that died centuries ago. But the cosmic ray story isn't just about solitary protons or electrons. It's also about entire atoms stripped of their electrons and hurled across the galaxy at nearly the speed of light. We now encounter the enigma of the ultra-heavy nuclei. Imagine not just a single subatomic bullet, but a complete atomic nucleus of iron, or even gold and uranium, being accelerated to such phenomenal energy that it becomes a cosmic ray. These are not mere fragments, they are the building blocks of matter, and their presence in the cosmic ray flux forces us to ask a profound question. What kind of cosmic forge is powerful enough to not only create these heavy elements but then launch them on an interstellar journey? The very existence of these heavy nuclei tells a story of stellar life and death. Elements like carbon, oxygen, and silicon are forged in the nuclear furnaces of ordinary stars. But to create the truly heavy elements like iron and everything beyond it, you need something far more violent. The immense pressures and temperatures inside a massive star's final moments during a supernova explosion are one of the primary cosmic crucibles where these elements are synthesized. Even more extreme processes, like the collision of two neutron stars, are thought to be the primary source for the heaviest elements in the universe, including gold and platinum. So, when we detect a nucleus of iron or a rarer element like cobalt in the cosmic rays, we are quite literally catching a piece of shrapnel from a stellar catastrophe that occurred millions of years ago. However, creating these heavy elements is only half the battle. The other, equally challenging part is accelerating them. This is where the physics becomes truly staggering. An iron nucleus has 56 times the mass and 26 times the charge of a single proton. The mechanisms that accelerate cosmic rays, like shock waves from supernova remnants, are thought to work more effectively on particles with higher electrical charge. This means that an iron nucleus can, in theory, gain energy much more efficiently than a proton in the same environment. but it also requires an acceleration site of unimaginable power and stability to handle such a heavy projectile. The magnetic fields confining the particle must be extraordinarily strong to keep it from escaping before it reaches these incredible speeds. The fact that we detect these ultra-heavy nuclei at all suggests that the accelerators are not just powerful, but also incredibly robust, capable of processing the entire periodic table. Perhaps the most crucial clue hidden in these heavy cosmic rays is their relative abundance. By carefully measuring the ratio of different elements, how much silicon there is compared to iron, or how much oxygen compared to carbon, scientists can create a kind of cosmic fingerprint. They then compare this fingerprint to the elemental abundances found elsewhere, like in the gas of our own solar system, which represents a well-mixed sample of the galactic material from which our sun formed. The differences are revealing. The cosmic ray source material appears to be slightly enriched in heavier elements compared to the average solar system composition. This suggests that the cosmic rays are not coming from just anywhere, but are preferentially accelerated from material that has been recently processed by supernova. It's as if the accelerators are scooping up the freshly forged heavy elements from the debris of stellar explosions and giving them an extra kick. This forensic analysis points a strong finger at core collapse supernova as the dominant source for these heavy nuclei. The expanding shock wave from such an explosion plows through the surrounding interstellar medium, but it also sweeps up the material that was just ejected from the star itself, material that is freshly enriched with heavy elements. This creates a perfect scenario. The accelerator is surrounded by the very fuel it needs. Yet, the story may not be so simple. The abundances of some very rare, heavy elements hint that there might be multiple contributors to the cosmic ray population. For instance, the relative amount of certain radioactive isotopes could act as a clock, telling us how much time elapsed between the nucleus being created in a supernova and it being accelerated. Some data suggests this time might be surprisingly short, on the order of 100,000 years, which is a blink of an eye in cosmic terms, further strengthening the link to recent supernova. The mystery of the ultra-heavy nuclei ultimately connects the vast scale of galactic travel to the intimate details of nuclear physics. By studying these atomic fragments, we are doing more than just cataloging cosmic bullets. We are engaging in a form of galactic archaeology. Each iron or gold nucleus that strikes our atmosphere is a preserved relic from a specific type of stellar death, carrying with it information about the temperature, density, and dynamics of the explosion that created it. They are tangible evidence of the violent processes that constantly seed the galaxy with the heavy elements necessary for planets, and indeed for life itself. In a very real sense, we are made of star stuff, and the ultra-heavy cosmic rays are the messengers that remind us of our explosive origins, hurling the very ingredients of worlds across the light years. Yet, even as we find mounting evidence that supernova remnants are our galaxy's primary particle accelerators, a specific and nagging gap remains in our understanding, a challenge known to astrophysicists as the Pevatron problem. The name itself comes from a unit of energy, the petaelectronvolt, which is 1,000 times more powerful than the energies reached in the Large Hadron Collider. A Pevatron, then, is any natural cosmic engine capable of boosting particles to this staggering threshold. For a long time, our models have pointed to supernova remnants as the most likely candidates to fill this role. The math seems to work. The total energy released in a typical supernova explosion, spread across its expanding shock wave, is more than sufficient to account for the flux of PV particles we observe. The paradigm is elegant and theoretically sound, but turning that theoretical certainty into an observational confirmation has proven to be one of the most stubborn challenges in modern astronomy. The heart of the problem lies in the specific and definitive signature we need to see. As we discussed, when an accelerated proton collides with a stationary proton in the interstellar medium, it produces a neutral pion that rapidly decays into 2 gamma-ray photons. The energy of these gamma rays is a direct reflection of the energy of the proton that created them. To prove that a supernova remnant is a genuine pevatron, we need to detect gamma rays with energies reaching up to 1 petaelectronvolt, which would be the unmistakable fingerprint of a parent proton possessing many times that energy. This is the smoking gun. For years, telescopes have been scanning the most promising, young, and energetic supernova remnants, detecting plenty of gamma rays, but almost always with energies that top out just short of the critical PV mark. It's as if we have found the factory. We can see the machinery at work, but we haven't yet caught it producing its very highest grade product. This absence creates a frustrating paradox. We are surrounded by cosmic rays with PV energies, and we have strong circumstantial evidence pointing to supernova remnants, but the definitive, conclusive link remains just out of reach. Why has this proof been so elusive? One significant factor is the age of the accelerator. The process of particle acceleration at a shock wave isn't instantaneous. It takes time for particles to be boosted to the highest energies. For a supernova remnant, the most powerful acceleration likely occurs during a specific phase of its expansion, when the shock wave is still strong and fast-moving, but has also swept up enough surrounding material to create a robust and turbulent environment. If we observe a remnant too early, the acceleration mechanism may not have had enough time to push particles to the PV limit. If we observe it too late, after the shock wave has slowed down considerably, the accelerator may have effectively turned off, no longer capable of reaching those extreme energies. We are therefore looking for a cosmic sweet spot, a relatively brief window in the multi-thousand-year lifespan of a stellar explosion where conditions are perfect for PV production. Catching a remnant in this exact phase requires both advanced instrumentation and a significant amount of astronomical luck. Another complicating factor is escape. The most energetic particles, once they reach PV levels, may not stick around for us to observe their telltale gamma-ray signature. The magnetic fields that confine particles within the remnant have a maximum strength. A proton with PV energy has so much momentum that it can potentially break free from these magnetic confines before it has a chance to collide with a gas atom and produce the gamma rays we're looking for. These particles would then escape into the wider galaxy, becoming the diffuse background of cosmic rays that we measure, but they would leave their source without providing the definitive proof we seek. In this scenario, the remnant is indeed a pevatron, but it effectively expels its highest energy products immediately, making them incredibly difficult to trace back to their origin. The very process we are trying to observe might be hiding its most dramatic results from our view. The pursuit of a confirmed pevatron has driven the development of a new generation of telescopes specifically designed to see the universe at these extreme energies. Ground-based arrays like the High-Altitude Water Cherenkov Gamma Ray Observatory in Mexico and the upcoming Cherenkov Telescope Array are pushing the boundaries of sensitivity. They are not just looking for a signal, but for the precise shape of the gamma ray spectrum at the highest energies, searching for a cutoff that would indicate the maximum energy achievable at the source. Recently, there have been tantalizing hints. The Lhasa Observatory in China has reported detecting gamma rays with energies exceeding 1 petaelectronvolt from several regions within our galaxy, including the direction of a few known supernova remnants. While this is incredibly promising, the challenge remains to pinpoint the emission unequivocally to the shock wave of the remnant itself, rather than to other complex environments like dense clouds of gas that the shock wave might be illuminating. The hunt is closing in, but the final piece of the puzzle, a clear, uncontested detection of PV gamma rays from a specific supernova remnant, would be a landmark moment, finally closing the loop on a mystery that has persisted for decades and solidifying our understanding of the cosmic engines that power the high-energy universe. But the influence of these cosmic projectiles extends far beyond grand questions of astrophysics and climate, reaching into the most intimate and tangible aspects of our modern technological world. While you might never feel a cosmic ray, there is a very real chance you have already experienced its effects, perhaps in the form of a mysterious computer crash, a corrupted file, or a sudden glitch in a video game. This is not science fiction. It is a daily reality for engineers who must contend with a phenomenon known as a single event upset, or SEU, where a single particle from the depths of space can silently, randomly, and instantly alter the digital reality of our machines. At its core, the process is a stunningly simple collision of the cosmic and the microscopic. The vast majority of a cosmic ray's journey is through empty space, but when it finally encounters the dense material of a silicon computer chip, its trip comes to a violent end. The particle, often a high-energy proton or a heavy atomic nucleus, slams into the intricate lattice of the semiconductor. This impact creates a tiny but dense trail of electrical charge, like a miniature lightning bolt surging through the chip's microscopic pathways. If this burst of charge happens to strike a sensitive node, such as a memory cell that is storing a single bit of data as an electrical charge, it can be enough to flip that bit. A 1 stored in memory can inexplicably become a 0 or vice versa with no other warning. This is a single event upset, a fundamental change to digital information caused by a direct hit from a subatomic bullet that has been traveling for millions of years. For everyday consumer electronics, these upsets are usually just a minor nuisance. They might cause a smartphone app to freeze momentarily or a saved document to develop a strange character. The system is typically designed to recover with a simple reboot. However, as the components in our computers have shrunk to unimaginably small scales, the problem has grown exponentially more severe. The transistors on a modern chip are so tiny that the electrical charge needed to represent a single bit is correspondingly minuscule. This means it takes less and less energy from an incoming particle to cause a bit flip. A cosmic ray that would have passed harmlessly through a larger, older chip from the 1980s can now easily disrupt the operation of a state-of-the-art processor. We have effectively built more sensitive targets for the universe's constant bombardment. It is in the realms of aviation, spaceflight, and critical data infrastructure that this issue transforms from a curiosity into a serious engineering challenge with life-or-death consequences. At high altitudes, the Earth's protective atmosphere is thinner, and the flux of cosmic rays is significantly higher. A single event upset in the flight control computer of a commercial airliner could, in theory, provide erroneous data to the autopilot. To mitigate this, aviation systems rely on robust redundancy. Critical flight computers are often triplicated, and their outputs are constantly compared. If one computer suffers a bit flip and produces an anomalous result, the other two can outvote it and isolate the faulty unit, ensuring the plane continues to fly safely. This is a direct and necessary response to the invisible rain of particles from space. The challenge is even more extreme for spacecraft operating outside the relative safety of Earth's magnetic field. In the deep space environment, satellites and interplanetary probes are exposed to the full brunt of galactic cosmic rays and occasional solar particle storms. A memory error could lead to the loss of precious scientific data or, in a worst-case scenario, cause a permanent failure of the vehicle. The famous example of the Mars rover Spirit encountering a persistent memory issue in 2010 is often discussed as a potential, though not confirmed, case of cosmic ray-induced damage. To combat this, space-grade electronics are often hardened against radiation. This can involve using special semiconductor designs that are less susceptible to charge buildup, or simply employing older, larger transistor technology that is inherently more robust, trading raw processing speed for increased reliability in the harsh environment of space. Perhaps the most concerning arena is that of critical data systems, particularly the massive server farms that power our financial networks, healthcare records, and global internet infrastructure. A random bit flip in a banking server could theoretically alter a financial transaction. A corrupted bit in a cloud storage facility could silently damage an archive of irreplaceable data. In 2014, a study even suggested that a significant number of unexplained network outages in large data centers could be attributed to cosmic rays. While the probability for any single server is low, when you have millions of servers running constantly for years, these rare events become statistically inevitable. This has led to the implementation of advanced error-correcting code memory in critical servers, which can automatically detect and fix single-bit errors, providing a crucial layer of defense against these cosmic interferences. The silent, invisible rain of cosmic rays is no longer just an astronomical phenomenon. It is a variable that must be factored into the design, operation, and resilience of the very technology that defines our modern civilization. This journey into the most powerful cosmic rays has taken us across the galaxy and beyond, but one of the most startling clues to their nature comes not from deep space, but from deep within the Earth's own historical record. In the year 774 and again in 775, something extraordinary happened in the skies above our planet. No human chronicler of the time wrote of a brilliant new star or a days-long celestial display. The events of those years, as far as historical texts are concerned, were entirely terrestrial. Yet a hidden message was being written, not on parchment, but in the very fabric of life itself. It would take over 1,200 years for us to learn how to read it, revealing that our planet was struck by a wave of radiation so intense that it has no parallel in recorded human history. The discovery began not with a telescope, but in a laboratory. Scientists studying ancient cedar trees in Japan were conducting a routine analysis of carbon-14 levels within the tree's annual growth rings. Carbon-14 is a radioactive isotope that is constantly produced in the upper atmosphere when cosmic rays strike nitrogen atoms. This carbon is then absorbed by living organisms, and its concentration in a tree ring provides a snapshot of cosmic ray intensity for that specific year. As the researchers moved from ring to ring, they expected to see the normal, gentle fluctuations caused by the sun's 11-year cycle. But when they reached the ring corresponding to the year 775, they were stunned. The level of carbon-14 spiked dramatically, increasing by nearly 20% in a single year. This was not a gentle fluctuation. It was a vertical cliff on their graph, an increase about 20 times greater than the normal variation caused by the solar cycle. It was as if, for a brief period, the cosmic ray dial had been cranked to an unprecedented setting. To confirm this was not a local anomaly, researchers turned to a second, independent natural archive, ice cores from Antarctica. Deep within the pristine ice layers, they measured the concentration of another isotope, beryllium-10, which is also created by cosmic ray interactions in the atmosphere. Just as with the carbon-14 in the Japanese cedars, the Antarctic ice revealed a massive, sharp peak in beryllium-10 deposition, precisely aligned with the years 774 and 775. This dual signal found in both hemispheres was the smoking gun. It confirmed that the entire planet had been bathed in an intense, short-lived blast of radiation. The event was global and it was powerful. Calculations based on the isotope spike suggest that in less than a year, Earth received a dose of radiation equivalent to 10,000 years worth of normal cosmic ray background. The immediate question was, what kind of cosmic event could possibly deliver such a devastating, yet seemingly invisible, punch? The detective work to identify the culprit began by ruling out the usual suspects. A nearby supernova was an obvious first guess. A stellar explosion would flood the solar system with cosmic rays, and a sufficiently close one could account for the isotope spike. However, there is a problem with this theory. A supernova close enough and bright enough to produce such a radiation surge would have been a spectacular sight in the night sky. It would have outshone Venus and possibly even been visible during the day for weeks. Yet, not a single astronomical record from that era from any civilization around the world, be it in Europe, Asia, or the Middle East, mentions the appearance of a brilliant new star. While it is possible that a supernova could have occurred in the daytime sky or been obscured by cosmic dust, the complete lack of any historical observation makes this explanation difficult to accept. This absence of a visual record pointed investigators toward a different, more terrifying possibility: a solar superflare. Our sun is capable of powerful eruptions called solar flares, but the event needed to explain the 775 anomaly would have to be thousands of times more powerful than anything we have observed in the modern era. A flare of such magnitude, while theoretical, would have been aimed directly at Earth, unleashing a torrent of protons and other particles. The isotope signature would be a perfect match. However, such an event would almost certainly have had other dramatic consequences. It would have triggered a global auroral display so intense that the night sky would have glowed a brilliant, bloody red, visible even at the equator. It likely would have severely damaged the ozone layer and potentially caused widespread electrical grid failures had one existed at the time. While there are no direct records of such an aurora from 775, some researchers have pointed to a cryptic entry in an Anglo-Saxon chronicle that describes a red crucifix appearing in the heavens after sunset, which could be interpreted as an unusual auroral event. The third, and perhaps most exotic, candidate is a gamma-ray burst. If a nearby star within our galaxy had undergone this cataclysmic event and its narrow, intensely focused jet had happened to be pointed directly at Earth, the energy delivered could easily account for the isotope spike. A gamma-ray burst would be a brief flash of high-energy photons, lasting from seconds to minutes, and would not leave a lingering, visible afterglow like a supernova. This could explain why no one saw a new star. The main event would have been over in a flash. The radiation would have ripped apart molecules in the upper atmosphere, creating the surge of carbon-14 and beryllium-10, and could have caused significant damage to the ozone layer. The terrifying aspect of this theory is that a gamma-ray burst from a source even a few thousand light-years away could pose an existential threat to life on Earth, making the mystery of the 775 event not just a historical curiosity, but a sobering reminder of our vulnerability to cosmic violence. To this day, the cause of the 775 anomaly remains an open and hotly debated mystery. Each explanation carries its own compelling evidence and its own significant challenges. The event stands as a unique marker in time, a testament to the fact that the Earth's history is inextricably linked to the violent cosmos. It demonstrates that cosmic rays are more than just a scientific abstraction. They are a tangible force that has, on at least one occasion, left an indelible mark on our planet's biosphere. The silent testimony of the tree rings and ice cores forces us to look up at the quiet sun and the peaceful stars with a new sense of caution, knowing that the universe is capable of unleashing a fury that can reach across the light years and etch its signature into the very rings of an ancient tree. Now, let's shift our perspective from the grandest explosions to a much more familiar object in our sky and explore a clever technique that turns it into a fundamental scientific instrument. This brings us to the fascinating phenomenon known as the cosmic ray shadow of the moon. It sounds like a concept from science fiction, the idea that the moon could cast a shadow not just with light, but with a rain of invisible particles. Yet, this is a real and powerful method used by physicists to calibrate their most sensitive detectors and to probe the invisible magnetic landscape of our galaxy. The principle is beautifully simple in theory. Cosmic rays, being a form of matter, should travel in nearly straight lines from their distant sources. Just as the moon blocks the light from stars and the sun during an eclipse, it should also block any cosmic rays coming from directly behind it. If you have a detector on Earth capable of mapping the directions of incoming cosmic rays, you would expect to see a deficit, a dark patch, in the part of the sky obscured by the moon. This shadow would be a perfect, sharp circle, confirming that the particles are arriving in straight lines and that the detector is perfectly calibrated to pinpoint their origins. But when scientists first went looking for this shadow with early detectors, they found something surprising. The shadow wasn't there, or more precisely, it was there, but it was incredibly faint and blurry, like a silhouette seen through frosted glass. The clear, sharp deficit they expected was smeared out and shifted slightly from the moon's actual position. The reason for this blurring gets to the very heart of a challenge we've encountered throughout our journey: magnetic fields. Cosmic rays are not photons of light, they are charged particles, primarily protons. As these charged particles journey across the galaxy, they don't travel in perfectly straight lines. They are constantly nudged and bent by the incredibly weak but pervasive magnetic fields that are threaded through the interstellar medium. Think of it as trying to walk in a straight line during a heavy crosswind. You'll constantly be pushed off course. A cosmic ray traveling from a distant source to the Earth is deflected by these galactic magnetic fields throughout its multi-million-year journey. By the time it reaches the vicinity of the moon, its path is no longer a direct line from its origin. This means that when the moon tries to block it, the particle may have already been deflected enough to miss the moon entirely, or conversely, a particle that should have missed the moon might be deflected into the shadow region. The result is that the moon's sharp shadow is smeared into a faint, broad dimple in the cosmic ray flux. This apparent complication, however, is where the true genius of the method lies. Scientists realized that the blurriness of the shadow isn't a problem to be solved. It's a measurement to be exploited. The amount of smearing and the precise displacement of the shadow from the moon's optical position are not random. They are direct consequences of the strength and orientation of the magnetic fields that the cosmic rays passed through on their way to us. By meticulously measuring the exact size and shape of the moon's cosmic ray shadow, researchers can effectively work backwards. It's like analyzing the pattern of ripples around a pole in a flowing river to calculate the speed and turbulence of the current. A larger, more diffuse shadow suggests that the particles were deflected more significantly, indicating the presence of stronger magnetic fields along their path. A shadow that is shifted to one side reveals the dominant direction of those magnetic fields in our local galactic environment. This technique has been refined over decades using massive detector arrays like the Tibet Air Shower Array and the Pierre Auger Observatory. These facilities have thousands of sensors spread over vast areas, allowing them to create high-resolution maps of the cosmic ray sky. With this precision, they can detect the moon's shadow with great statistical significance. The findings are profound. The observations confirm that the typical deflection for a high-energy cosmic ray is quite small, on the order of a fraction of a degree, but it is measurable. This helps to put quantitative constraints on the average strength of the galactic magnetic field, a value that is notoriously difficult to measure by any other means. It tells us that the space between the stars is not a perfect void, but is laced with a faint magnetic skeleton that guides the journey of these high-energy messengers. So, the next time you look up at the moon, consider that it is more than a world of rock and dust. It is a natural collaborator in a grand cosmic experiment, its silent presence helping us to map the invisible forces that weave through the galaxy and shape the paths of the universe's most energetic particles. But what if the cosmic rays we've been discussing are not just protons or atomic nuclei, but something far more bizarre, specks of an entirely new form of matter that could unravel the very fabric of reality? This brings us to the edge of theoretical physics, to a cosmic ray enigma that is less about where these particles come from and more about what they actually are. We now venture into the realm of the truly exotic, to the possibility that mixed in with the familiar atomic shrapnel are hypothetical objects known as strangelets. Imagine a particle that is not made of the usual protons and neutrons, but is instead a single, ultra-dense nugget composed of a soup of quarks, including a type known as strange quarks. This is the essence of a strangelet, a theoretical form of matter so stable and so dense that it could represent the true, fundamental ground state of all matter in the universe. To grasp why this is such a revolutionary idea, we need to understand the hierarchy of matter. The atoms that make up our world are composed of a nucleus of protons and neutrons, which are in turn made of smaller particles called quarks. Protons and neutrons each contain 3 quarks bound together by the strong nuclear force. This structure is stable here on Earth, but physicists have long theorized that under conditions of immense pressure and density, like those inside a neutron star, this familiar arrangement might break down. The incredible gravitational crush could overcome the forces that keep protons and neutrons separate, causing them to dissolve into a vast, uniform sea of quarks, a state known as quark matter. Within this soup, a new equilibrium could be reached if a certain type of quark, the strange quark, were to join the mix. This strange quark matter could be more stable than even the iron at the core of a planet, meaning it would never decay. A chunk of this material, a strangelet, could theoretically be stable forever. The cosmic connection is what makes this idea so captivating. If strange quark matter is indeed the most stable form of matter, then neutron stars could be incubators for it. During a violent event like the collision of 2 neutron stars, a fragment of this ultra-dense strange matter could be blasted away into space. If it were stable enough to survive the journey, it would travel as a cosmic ray, an exotic bullet unlike any other. It would be astronomically dense. A strangelet the size of a dust grain could have the mass of a small mountain. If such an object were to strike the Earth's atmosphere, it would not create a typical particle shower. Instead, its immense density would allow it to punch through the air almost unaffected, plummeting towards the ground like a microscopic meteorite. It would be a relic of the most extreme conditions in the universe, a piece of a neutron star's heart delivered to our doorstep. The implications of detecting a strangelet would be nothing short of earth-shattering for physics. It would confirm the existence of an entirely new phase of matter, proving that our everyday reality is just a metastable state and that a more fundamental, stable form of matter exists. This would radically alter our understanding of nuclear physics and the ultimate fate of dense matter in the cosmos. It would also provide direct insight into the interior composition of neutron stars, suggesting they might not be neutron stars at all, but rather quark stars composed largely of this strange matter. The discovery would open up a new field of study, potentially offering clues about the early universe moments after the Big Bang, when all matter may have existed in a similar quark-gluon plasma state. However, the very properties that make strangelets so fascinating also make them nearly impossible to detect with conventional cosmic ray observatories. These detectors are designed to measure the cascading showers of particles created when a high-energy proton or nucleus collides with an air molecule. A strangelet, due to its incredible density and stability, would behave completely differently. It would be a heavily ionizing particle, tearing electrons from atoms as it passes through the atmosphere, but it would not necessarily create a large, diffuse shower that our arrays are optimized to see. Its signature would be a very narrow, penetrating track of ionization, a signal that could easily be mistaken for a heavy, ordinary atomic nucleus or dismissed as instrumental noise. Distinguishing a strangelet from, say, a uranium nucleus requires exquisitely precise measurements of its charge-to-mass ratio and its interaction behavior, a task at the very limit of our technological capabilities. This immense challenge has led scientists to get creative in their search. Some experiments, like those using old meteorites as natural particle detectors, have scoured these ancient rocks for traces of strange-alert impacts that would have left unique damage trails over millions of years. Others have looked for the unique signals strange alerts might produce in dedicated underground detectors. The speculation even extends to the possibility that strange alerts could be dangerous. In a far-fetched but popular science fiction scenario, a strange alert could be strange matter in the literal sense, capable of converting any ordinary matter it touches into more strange matter upon contact, triggering a chain reaction that could transform the entire Earth. Thankfully, most theoretical models suggest that if strange alerts exist, they would likely carry a positive electrical charge, causing them to repel atomic nuclei rather than merge with them, making this apocalyptic scenario highly improbable. The hunt for strange alerts in the cosmic ray flux remains one of the most speculative pursuits in modern physics. It is a search for a needle in a haystack when we aren't entirely sure what the needle looks like, or even if it exists at all. Yet the potential reward is so profound that the search continues. It represents the ultimate cosmic detective story, where a single, anomalous signal buried in trillions of ordinary events could unveil a new law of nature and change our perception of reality itself, proving that the universe's greatest secrets might be carried on the most unusual of messengers. As we've journeyed through the signatures of stellar remnants and the possibility of exotic particles, our path now leads us to a mysterious glow that envelops the very heart of our galaxy. When the Planck satellite and the Fermi Gamma Ray Space Telescope turned their sensitive instruments toward the center of the Milky Way, they mapped the sky not just in visible light, but in microwaves and gamma rays. What they found was unexpected and perplexing: a vast fog-like emission, a haze of energy that balloons out from the galactic core for thousands of light years in two enormous lobes. This phenomenon, officially dubbed the Fermi bubbles in gamma rays and the microwave haze in Planck's data, represents one of the most significant and puzzling large-scale structures in our own celestial backyard. The mystery lies not in its existence but in its origin. What cosmic process is powerful enough to inflate these gigantic bubbles and fill them with this persistent, diffuse light? The leading suspects are populations of high-energy electrons, and their source is a question that pits the known violence of stellar life cycles against the tantalizing unknown of dark matter. To understand the puzzle, we need to look at how this haze is created. The microwave emission observed by Planck has a specific signature. It is synchrotron radiation. This is the light given off when high-energy electrons, spiraling at near light speed, are forced to dance through magnetic fields. The powerful magnetic fields that thread the galactic center whip these electrons around, causing them to lose energy by radiating it away as microwaves. Meanwhile, the gamma-ray glow seen by Fermi is likely produced by those same electrons through a different process called inverse Compton scattering. Here, the energetic electrons collide with lower-energy photons, such as those from the starlight bathing the galactic center, and boost them up to much higher gamma-ray energies. So the combined picture is clear. The haze is the product of a vast population of relativistic electrons trapped within the Fermi bubbles. The real enigma is identifying the engine that accelerated them to such incredible speeds in the first place. One compelling explanation points to a dramatic chapter in our galaxy's history, a period of intense activity that has since quieted. Astronomers call this the starburst scenario. Imagine the galactic center not as it is today, but as it was several million years ago, witnessing a ferocious burst of star formation. Hundreds of thousands of massive stars could have been born in a relatively short cosmic time span. These stars would have lived fast and died young, exploding as supernova in a veritable fireworks display of stellar death. The collective effect of all these explosions and the powerful stellar winds from the massive stars would have been like a cosmic hurricane. This relentless energy output could have blown a giant pressurized bubble of hot gas outwards, perpendicular to the galactic disk, creating the very lobes we see today. Within the turbulent shock fronts of this expanding bubble, electrons would have been efficiently accelerated to the high energies needed to produce the observed synchrotron haze. In this view, the haze is a fossil, the fading aftermath of a forgotten era of extreme stellar activity at the heart of the Milky Way. However, a competing and far more exotic hypothesis suggests that the source of the electrons might not be stellar at all, but something fundamentally invisible. This is the dark matter annihilation model. We know that a vast halo of dark matter surrounds our galaxy, and its density is thought to be greatest at the galactic center. If dark matter consists of particles that are their own antimatter counterparts, then when two of them collide, they could annihilate each other, converting their mass directly into energy and producing a shower of standard model particles, including electrons and positrons. This process would inject a steady stream of high-energy electrons right into the galactic core, which would then get trapped by magnetic fields and radiate the synchrotron glow we see as the haze. The beautifully symmetric, smooth appearance of the haze could be a natural consequence of the smooth, spherical distribution of the dark matter halo, making this an elegant, if unproven, explanation. Distinguishing between these two scenarios, a past starburst or ongoing dark matter annihilation, is a major focus of modern astrophysics. The key may lie in the precise details of the haze structure and spectrum. A starburst-driven bubble would likely have sharper, more defined edges, corresponding to the forward shock of the expanding wind. The energy distribution of the electrons might also show telltale signs of being powered by a relatively short, violent event. A dark matter signal, on the other hand, might be smoother and more diffuse, with a specific energy signature in the gamma-ray spectrum that matches the predicted mass of the dark matter particle. Recent, more detailed observations have added further intrigue. The edges of the Fermi bubbles appear remarkably sharp, which is somewhat more consistent with a single, powerful outburst than with a continuous process like dark matter annihilation. Yet the debate is far from settled. The galactic center is an immensely complex environment, and disentangling the haze from all the other emission sources is a monumental task. The mystery of the galactic haze thus stands as a powerful reminder that even the most familiar places in the cosmos can hold profound secrets, forcing us to choose between the spectacular violence of stars and the silent, pervasive influence of the universe's most dominant but hidden substance. While the mysteries of cosmic rays captivate us from the safety of Earth, they present a starkly different and more urgent challenge for the future of human spaceflight. Venturing beyond the protective cocoon of our planet's magnetic field and atmosphere means entering a realm of constant, invisible bombardment. A journey to Mars, a multi-month voyage through the void, would expose astronauts to a radiation environment for which our biology is profoundly unprepared. The primary threat comes not from the sun's occasional outbursts, but from the steady, relentless drizzle of galactic cosmic rays, atomic nuclei, accelerated to near light speed that can pierce through spacecraft hulls and human tissue alike. The danger these particles pose is uniquely insidious. Unlike the lower energy radiation we might encounter in medical settings, a single galactic cosmic ray nucleus carries a tremendous amount of energy. When it slams into the delicate strands of DNA within a cell, it doesn't just cause a simple break. It creates a concentrated blast of damage, shattering the DNA molecule in multiple places and making it far more difficult for the cell's repair mechanisms to fix the error correctly. This can lead to cell death or worse, mutations that increase the long-term risk of cancer. Beyond cancer, studies suggest that this type of radiation exposure could also lead to cataracts, heart disease, and even cognitive degeneration over time, potentially clouding an astronaut's mind during a critical mission. The sheer penetrating power of these particles makes them a nightmare to shield against. A typical aluminum spacecraft hull, which might block lower energy radiation, is almost transparent to a high-energy iron nucleus. It's like trying to stop a bullet with a sheet of paper. The particle blasts through, and in the process, it can even create a secondary shower of harmful fragments as it collides with the atoms in the hull itself. This has forced engineers and scientists to think far beyond traditional shielding. One of the most visionary concepts involves creating an artificial magnetic field around the spacecraft, a miniature replica of Earth's own magnetosphere. The idea is to generate a powerful magnetic bubble that would deflect the charged cosmic rays away from the crew compartment, much like a real force field from science fiction. While the physics is sound, the practical challenges are immense. Generating a magnetic field strong enough to be effective would require massive amounts of power and sophisticated superconducting magnets, both of which add significant weight, complexity, and energy demands to a spacecraft that must be as efficient as possible. Researchers are actively working on scaled-down prototypes, but a full-scale system remains a prospect for the future. A more immediately plausible approach involves using advanced materials as passive shielding. Instead of just aluminum, spacecraft hulls could be lined with layers of hydrogen-rich materials, such as certain plastics or water. Hydrogen is the most effective element for blocking cosmic rays because its tiny nucleus is less likely to produce those dangerous secondary particles when struck. Imagine the walls of a Mars transfer vehicle being integrated with its water storage tanks, creating a life-saving barrier from a vital resource. Another intriguing idea is the use of polyethylene, a common plastic that is exceptionally rich in hydrogen. Experiments on the International Space Station have already tested panels of this material to assess its protective qualities. There's even research into more exotic substances like hydrogenated boron nitride nanotubes, which combine lightweight strength with superior shielding properties. The solution will likely be a combination of these approaches: smart spacecraft design that maximizes the placement of supplies and equipment to act as radiation barriers, coupled with selectively placed advanced materials in the crew's living quarters. Ultimately, solving the cosmic ray threat is a fundamental prerequisite for the long-term exploration and settlement of the solar system. It's a complex puzzle with no single easy answer, blending cutting-edge physics, material science, and human physiology. Every new discovery about the origins and nature of these high-energy particles doesn't just deepen our understanding of the cosmos. It directly informs the technologies we must develop to survive within it. The enigmatic cosmic rays that have guided our quest to understand the universe's greatest explosions may also hold the key to determining whether humanity can safely journey to the stars beyond our world. But to truly solve the mysteries we've been exploring, we need more than just historical data or statistical hints. We need an instrument of unparalleled power, one capable of seeing the high-energy universe with a clarity we've only dreamed of. That future is now taking shape on two continents with the construction of the Cherenkov Telescope Array, or CTA, a project that represents a quantum leap in our quest to understand cosmic rays and their violent origins. The underlying principle is both elegant and ingenious, building on a technique perfected by earlier observatories. When a high-energy gamma ray from a distant cosmic accelerator travels across space and slams into the Earth's atmosphere, it doesn't reach the ground. Instead, it triggers an avalanche. The gamma ray's energy is converted into a cascade of secondary particles, electrons and positrons, moving faster than the speed of light in air. This superluminal motion, while impossible in a vacuum, is allowed in a medium like our atmosphere, and it produces a fleeting, ethereal glow known as Cherenkov radiation. It's a faint, bluish flash of light that lasts for just a few billionths of a second, invisible to the naked eye. The CTA is designed to be the ultimate catcher of this ghostly light. Instead of relying on a few large telescopes, it will be a massive array of over 100 telescopes of 3 different sizes, spread across vast areas in the northern hemisphere in La Palma, Spain, and the southern hemisphere in the Atacama Desert of Chile. This multi-site approach allows it to scan the entire celestial sphere, from the dense galactic plane visible from the south to the extragalactic sources prominent in the north. The true revolution of the CTA lies in this stereo vision. When a single telescope detects a Cherenkov flash, it can tell you that an event occurred, but pinpointing the exact energy and direction of the original gamma ray is difficult. With the CTA's coordinated network, multiple telescopes will see the same air shower from slightly different angles. By combining these viewpoints, like our brains use two eyes to perceive depth, the array can triangulate the shower's path with breathtaking precision. This stereoscopic view allows scientists to reconstruct the properties of the initial gamma ray with an accuracy that is an order of magnitude better than any existing facility. It will be like moving from a grainy black and white photograph to a high-definition, three-dimensional movie of particle physics happening 100 kilometers above our heads. This leap in sensitivity and resolution is what will allow the CTA to tackle the core mysteries head-on. In the hunt for the elusive pevatrons, the CTA won't just see a blur of gamma rays from a supernova remnant. It will be able to map the emission with such detail that it can pinpoint the exact location of the acceleration within the remnant's shock wave. It will measure the energy spectrum of the gamma rays with such fidelity that it can definitively distinguish between the signature of accelerated protons and that of electrons, finally providing the smoking gun for the supernova remnant paradigm. For the first time, we will be able to confidently identify which galactic objects are capable of producing particles at the petaelectronvolt frontier and understand the precise physical conditions that make it possible. Beyond our galaxy, the CTA's power will transform our search for the sources of ultra-high-energy cosmic rays. While the CTA itself detects gamma rays, which are neutral and travel in straight lines, they are often produced alongside the protons and atomic nuclei that make up cosmic rays. By creating a highly detailed map of the most energetic gamma ray sources in the universe, the CTA will provide a clean, unambiguous catalog of potential cosmic ray factories. When a particle detector like the Pierre Auger Observatory records an ultra-high-energy cosmic ray, astronomers will be able to cross-reference its rough arrival direction with the CTA's crisp map. If a brilliant gamma-ray source, like an active galactic nucleus or a gamma-ray burst remnant, lies within that error circle, the connection will be far stronger than any statistical correlation we have today. The CTA acts as the sharp-sighted guide that can point the way for other experiments, turning blurred suggestions into firm identifications. Furthermore, the array's ability to probe fundamental physics is staggering. By observing distant active galaxies, the CTA will measure how gamma rays of different energies are attenuated by the extragalactic background light, the cumulative starlight from all the galaxies in the universe. This will allow us to map the history of star formation in a completely novel way. It will also search for the unique gamma-ray signatures predicted by theories of dark matter, potentially seeing the faint glow from the annihilation of these mysterious particles in nearby dwarf galaxies or the galactic center. The CTA is more than a telescope. It is a gateway to a new era of exploration, one that promises to not only find the cosmic accelerators we've long sought, but to use their extreme energy to test the very laws of physics under conditions impossible to recreate on Earth. It is our best hope for turning the enigmatic whispers of cosmic rays into a clear, declarative understanding of the universe's most powerful phenomena. And so our journey through the cosmos's most powerful and puzzling messengers draws to a close. We have ventured from the incomprehensible energy of the oh my god particle, a single speck of matter carrying the force of a major league fastball, to the eerie silence of the voids from which particles like Amaterasu seem to emerge. We have seen how these invisible bullets are not just abstract curiosities but forces that shape our world, from leaving their mark in ancient tree rings to causing glitches in our most advanced technology. Each of these 25 enigmas is far more than a date, a point on a graph. It is a doorway, a profound question mark etched into the fabric of reality, challenging us to look deeper and think bigger. The true significance of these cosmic rays lies not in the answers we have, but in the questions they force us to ask. The hunt for their sources is a hunt for the universe's ultimate powerhouses, the supermassive black holes, the colliding neutron stars, the gamma-ray bursts that illuminate the cosmos for a few fleeting seconds. Yet, when the trail runs cold, pointing to empty space or defying known physics like the Anita anomalies, we are pushed to an even more thrilling frontier. We are compelled to consider whether we are witnessing the fingerprints of dark matter, the decay of cosmic strings, or perhaps phenomena that require a fundamental rewriting of Einstein's laws of relativity. Every anomalous particle is a direct challenge, a message from the cosmos that our current map of physics is incomplete and that wonders beyond our imagination await discovery. This is not the end of the story, but a vibrant and ongoing scientific revolution. The next chapter is being written right now by the next generation of observatories, like the Cherenkov Telescope Array, which will see the high-energy sky with unprecedented clarity. These tools will allow us to finally pinpoint the cosmic accelerators, to watch particles being born in the shocks of supernova remnants, and to perhaps even catch a glimpse of dark matter annihilation. The greatest discoveries are still ahead of us, waiting for the right combination of technology, ingenuity, and inspiration, and that inspiration could very well come from you. The mysteries of the cosmos belong to everyone, and the next revolutionary idea might be sparked by a curious mind watching a video like this, looking up at the night sky and daring to ask, what if? The universe is a grand, dynamic, and often violent place, and cosmic rays are our most direct connection to its most extreme realms. They remind us that we live within a constant, silent storm of unimaginable power, a storm that carries the secrets of creation itself. So, what cosmic mystery captivates you the most? Is it the sheer power of the oh my god particle, the haunting void origin of Amaterasu, or the technological intrigue of a single event upset? Share your thoughts in the comments below. We'd love to continue this conversation with you. And if you're ready to unravel more of the universe's deepest secrets, make sure to subscribe and hit the notification bell for our next journey into the cosmos. The adventure is just beginning.